14.7. That number is not a magnitude, it is not a temperature, and it is not a death toll. It is a measurement of how far the ground tipped underneath the most closely watched volcano in the United States over the course of a single afternoon this month. Here is what 14.7 means. Scientists measure ground tilt in units called microradians. 1 microradian is about the tilt you would get if you took a plank 1 mile long, laid it flat, and then lifted one end by roughly the thickness of a dime. That is the sensitivity we are talking about. So 14.7 microradians means the summit of Kilauea on the big island of Hawaii sagged by close to 1 inch across a mile of solid rock in about 8 hours. It sagged because something underneath it emptied out. And ever since that afternoon, it has been tipping back. That is the entire story of what is happening on Hawaii right now, and it is why the United States Geological Survey is telling people in plain language that the next eruption is likely within days, not years. Not sometime, days. As of the most recent modeling from the Hawaiian Volcano Observatory, the window for the next burst of lava fountains opens on the 27th of July and runs through the 31st. Kilauea has gone quiet. And the quiet is the countdown. I want to be careful with you from the first minute, because this is a topic where a lot of channels are going to shout at you this week. What is happening at Kilauea is not the end of Hawaii. It is not a supervolcano. It is not a warning sign for anything on the mainland. What it actually is turns out to be stranger and, honestly, more impressive than the panic version, because right now, Kilauea is the one volcano on this planet where scientists can tell you with real confidence which week it is going to erupt. That has almost never been possible in the history of volcanology. And the woman who built the method that makes it possible has said out loud that it will stop working. If you like your Earth science with the actual data attached and the exaggeration stripped out, subscribing takes 1 second, and it is the whole reason this channel exists. So let us go back to the 15th of July and reconstruct exactly what happened, because the details of that day are what set the clock that is running right now. The first sign came the day before. On the afternoon of July 14th, the north vent inside Halemaumau crater started overflowing. Not fountaining overflowing, low, sluggish spills of lava creeping out of the vent opening and onto the crater floor, the way a pot on a stove will slop over the rim before it truly boils. These precursory overflows are one of the most reliable tells at Kilauea. They mean the magma column inside the conduit has risen high enough to reach the lip. Observatory scientists watched them all evening. The following morning, around 8:30, the overflows stopped being overflows. The north vent opened up and began throwing molten rock into the air. Within a couple of hours, it was reaching about 950 feet above the ground. Picture 3 statues of liberty stacked one on top of another, base to torch, and then picture that column made entirely of liquid rock at somewhere near 2,000 degrees, roaring, being pushed by expanding gas. That was the peak of episode 51. The strange part was the south vent. It never fountained at all. It sat there and emitted flames and jets of gas, like a burner turned on next to a fire hose. 2 vents, a few hundred feet apart, fed from the same shallow reservoir, behaving completely differently on the same day. Nobody at the observatory will pretend they fully understand why. The plume climbed to roughly 18,000 feet above sea level. That is about 3.5 miles of ash, gas, and volcanic glass standing straight up over the island, which matters enormously to aviation and almost not at all to people on the ground, depending entirely on which way the wind is blowing that morning. On that particular morning, the wind was kind. The tephra, that is the catch-all word for everything a volcano throws through the air, from gritty ash to needle-thin strands of volcanic glass, fell mostly inside the closed area of Hawaii Volcanoes National Park, southwest of the vents, where nobody is allowed to be. A light fall of Pele's hair was reported at a few spots outside the closure, including the Yukahuna Overlook and the Cow Desert Trailhead along Highway 11. The observatory's final accounting noted no tephra reported from any populated areas. On a different wind day, that sentence would read very differently. And later in this video, I am going to show you exactly how differently. Then, At 4:46 in the afternoon, it stopped. Not faded, not tapered. The observatory's own word was abrupt. The north vent quit. 8.3 hours from start to silence. In that time, Kilauea erupted about 6.6 million cubic yards of lava. Try this for scale. If you took an American football field, end zone to end zone, and used it as the base for a column of that lava, the column would stand more than half a mile tall. That fresh lava covered somewhere around half of the crater floor. And the summit had sagged by 14.7 microradians. Now, why does the abruptness matter? Because it is the piece of this eruption that scientists openly admit they cannot explain. A fountain that dies over an hour makes intuitive sense. You are running out of pressure, running out of gas, running out of supply. A fountain 950 feet tall that simply switches off as if someone closed a valve is a different kind of problem. Researchers at the Hawaiian Volcano Observatory have said the question of why these episodes stop so decisively is one of the central puzzles of this eruption, and one that volcanologists will be studying for decades. 51 times now, Kilauea has done this. 51 times it has shut off, and the mechanism remains an open question. So the fountain ends, the summit is deflated, and the clock starts. Here is the part that makes this volcano unlike almost any other on Earth right now, and it is worth slowing down for. Think of Kilauea's shallow magma chamber as an account with a balance. During a fountaining episode, the volcano makes a withdrawal. Magma leaves the chamber contracts, the ground above it pulls inward and tilts down toward the summit. That is the deflation. During the pause that follows, deeper magma flows back up into the chamber and makes deposits. The chamber swells, the ground above it bulges, the tilt runs back the other way. That is inflation. At most volcanoes, that ledger is a mess. Deposits and withdrawals do not match. Magma leaks sideways into rift zones, or stalls, or arrives in unpredictable pulses. At Kilauea, since episode 5 of this eruption, the books have balanced almost perfectly. The amount of deflation during a fountaining episode has been followed by very nearly the same amount of inflation during the pause, which means each episode erupts roughly what the system saved up since the last one. And that, in turn, means there is a specific pressure, a specific balance in the account at which this volcano fountains. Hit the number, and it goes. The scientist who turned that observation into a working forecast is Ingrid Johansson, a research geophysicist at the Hawaiian Volcano Observatory. Her method leans on a borehole tiltmeter near Uwekahuna on the rim of the summit caldera, an instrument sensitive enough to feel that dime across a mile change. She has described the rule of thumb simply. The tilt needs to come back to roughly where it stood right before the last episode. Once the inflation has been running long enough to measure a reliable rate, you can extend the line forward and estimate when it crosses the target. That estimate is the forecast window. Johansson has also been blunt about how unusual this is. Speaking about the current sequence, she said that other episodic fountaining eruptions at Kilauea have not been this regular. Read that carefully, because it cuts both ways. It is the reason the forecasts work. It is also the reason they are temporary. This is not a permanent property of Kilauea. It is a phase. Johansson has been explicit that the ability to issue these windows will almost certainly end when the volcano's behavior changes, and volcanoes change their behavior. The forecast is not a law of nature. It is a pattern that has held for 51 rounds and could break on the 52nd. Which brings us to what the ledger has been doing since the 15th of July, and why the answer has been so unsettled. By the 20th, the refill had been smooth and steady. The observatory ran the models and published a window, episode 52 most likely, between the 24th and the 28th, with the 25th through the 27th flagged as the highest probability days. Clean signal, confident forecast. Then, the volcano did something inconvenient. Very early on Tuesday, the 21st, the inflation stopped. Just went flat for more than a day. The account quit accepting deposits. Inflation resumed Wednesday morning and picked up 2 more microradians, and by Thursday, the 23rd, the summit had recovered 11.1 of the 14.7 microradians it had lost. The observatory nudged the window to the 25th through the 29th. Then, over the following weekend, the tilt actually reversed. Deflation, again, during a pause, the opposite of what the model expects. By Saturday, the 25th, the observatory reported that deflation had been running for about a day and a half and pushed the window back once more. The 27th through the 31st, 3 forecasts in 6 days. Same volcano, same instrument, same method, 3 different answers. I want you to notice something about how that was handled, because it is the opposite of what you usually see. The observatory did not bury the revision. They published the reason in public every single morning. Here is the tilt. Here is what it did overnight. Here is why the window moved. Every one of those updates carries a line noting that further periods of slow inflation or deflation may shift the window again. That is what an honest forecast looks like. It is a range with a stated reason, not an appointment. If you have been watching those daily numbers this month, I would like to hear it. Drop a comment with what you noticed, because a surprising number of people now follow this tilt meter the way other folks follow a stock ticker. Now, let us deal with the fear directly, because it is out there and it deserves a straight answer. Kilauea is not a supervolcano. It never has been. It is a basaltic shield volcano, which is the runny, low-gas, relatively gentle end of the volcanic spectrum. Basalt lava flows. It does not typically detonate. The events that make Kilauea deadly historically have not been explosive blasts. They have been lava reaching places where people live. The current alert level for Kilauea is advisory, with an aviation color code of yellow, and the eruption is confined entirely to Halemaumau crater inside a closed section of Hawaii Volcanoes National Park. That closure is not new panic management. That stretch of caldera rim has been off limits to the public since late in 2007. Second, this is not 2018. That comparison gets made constantly, and it is wrong in an important way. In 2018, magma drained out of the summit and moved down the East Rift Zone, opening fissures in a residential subdivision. More than 700 structures were destroyed. The summit caldera collapsed as the reservoir emptied beneath it. That was a rift zone eruption, with a summit collapse a completely different plumbing scenario from what is happening now. Right now, the observatory reports that seismicity and ground deformation in both the East Rift Zone and the Southwest Rift Zone remain low, and sulfur dioxide emissions from the East Rift Zone are below the detection limit. Nothing is moving toward anybody's neighborhood. Third, and this is the one worth remembering, the fountains are not a sign of escalation towards something bigger. They are a sign of a system that has found a rhythm. A volcano that erupts 51 times in 19 months is a volcano that keeps relieving itself. The scenarios that worry volcanologists are usually the ones where pressure accumulates with nowhere to go, not the ones where the mountain empties its account on a schedule you can print on a calendar. So no, this is not the big one. What it is the best documented episodic fountaining eruption in recorded history, happening in real time, on live cameras, with a forecast window attached. That is remarkable enough without dressing it up, which is a good moment to talk about what actually drives these episodes, and to be honest about where the science runs out. Between fountains, Kilauea is not asleep. The seismic stations across the volcano keep recording tremor, a low-frequency rumbling produced by magma and gas moving through the conduits. During an episode, that tremor becomes intense. Between episodes, it drops way down, but it never disappears. Gas keeps venting, magma keeps stirring near the surface. The volcano stays lit even when nothing is visible. That is why the vents glow all night in the webcams during a pause, and why the observatory reports strong glow and occasional flames from the south vent in updates where the headline says paused. Then there is a phenomenon with a wonderfully mechanical name, the gas piston. Inside the conduit, gas bubbles accumulate underneath a slightly cooler, stiffer layer of lava near the top. The trapped gas pushes the whole column upward, the lava level in the vent rises, sometimes high enough to spill over the rim. Then the gas escapes, the column drops back down, and the cycle repeats. Rise, spill, drain, repeat. The observatory has documented several varieties of this during the current eruption. Some are visible on camera. Some happen too deep in the conduit to see, and are inferred only from wobbles in the tremor signal and the sulfur dioxide output. Gas pistoning has shown up as a precursor to full fountaining over and over in this sequence. Those overflows on the 14th of July, the day before episode 51, that behavior. When pistoning gives way to steady, continuous tremor, it tends to mean the gas-charged magma column has stopped cycling and started rising uniformly, and a fountain follows. And here is the honest limit. The observatory has stated plainly that it does not yet have a full understanding of why gas pistons so often precede high fountaining, or why they behave differently from one episode to the next. So we have a precursor that works empirically without a settled explanation, and an ending that abrupt shutoff that has no settled explanation either. We can time this eruption better than almost any eruption in history, and we still cannot fully say why it starts or why it quits. That gap does not make the forecasts unreliable. It makes them empirical. There is a real difference, and it is the difference between a weather forecast and a proof. Now, the scoreboard, because the numbers on this eruption have quietly become historic, it began on the 23rd of December, 2024, at about 20 past 2 in the morning. Episode 1 sent fountains to roughly 518 feet. Since then, it has run 51 episodes through the middle of July, which averages out to one about every 11 days, though the real spacing has swung from under a day to more than 3 weeks. Most episodes finish in less than 12 hours. On the 1st of June this year, episode 48 pushed the count past 47, which was the number of high fountaining episodes in the opening years of the Pu'u eruption between 1983 and 1986. Katie Mulliken, a geologist with the observatory, confirmed the milestone, the most fountaining episodes of any single eruption at Kilauea in the written record. Because the lava is coming from the same vents in the same crater, it counts as one continuous eruption, not 51 separate ones. The tallest fountain came on the 10th of March this year during episode 43. It started at 17 minutes past 9 in the morning and ran a little over 9 hours. Both vents went. The south vent reached 1,770 feet higher than the Empire State Building measured from the sidewalk to the tip of its spire, with more than 300 feet to spare. At its peak, the volcano was erupting roughly 1,000 cubic yards of lava per second. The plume punched past 30,000 feet above sea level, which is airliner territory, and the wind that day was not kind. Light southwest winds carried the plume north and east, straight over inhabited ground. Tephra, as large as 6 inches across, was reported at the volcano golf course community. Fine ash and Pele's hair reached as far as Hilo. Debris fell on communities up to 50 miles away. More than 200 tephra fall reports came in from residents. At the Kilauea military camp inside the park, the grass around the flagpole was completely buried. That is the real hazard of this eruption. Not lava at your door, airborne glass, and where the wind decides to put it. Volcanic glass sounds abstract until you handle it. Pele's hair is exactly what the name suggests. Filaments of lava stretched into strands as thin as human hair, light enough to ride the wind for tens of miles, sharp enough to irritate skin, eyes, and lungs. Reticulite is the foamy, feather-light version, and chunks of it, up to a foot across, have landed in residential areas during this eruption. It looks like a sponge, and it is made of glass. Then there is the problem you would never guess. A large share of households near the summit rely on rooftop rainwater catchment for their drinking water. Tephra lands on the roof, rain washes it into the tank. One of the main concerns is fluoride, which can coat tephra particles and then dissolve into the water. After the heavy fallout episodes, scientists and community volunteers went out and collected ash samples, rooftop runoff, and catchment tank water to understand what those deposits do to water quality. That is what a volcanic hazard looks like in a place where people actually live, not a river of fire, but a question about what came off your roof last Tuesday. And there is the gas. During an eruption, the summit releases sulfur dioxide at rates that typically vary somewhere between 1,000 and 5,000 tons per day. Downwind, that sulfur dioxide reacts in the atmosphere to make volcanic smog, which is a genuine respiratory problem for people with asthma, emphysema, or heart conditions across parts of the island. Vog is why a Kilauea eruption can send someone in Kona to a doctor without a single rock ever reaching them. Meanwhile, more than 157,000 people visited the park in a single month last November, a jump of over 40% from the same month the year before. So you have record crowds, live glass falling from the sky on the wrong wind day, and a monitoring team trying to tell everybody where to stand. Which brings us back to right now, and to what the observatory is actually watching this week. There is an honest complication in the monitoring itself. Recent power and storm-related outages knocked out several summit stations, and while the network has mostly recovered, some instruments, including one summit tiltmeter, remain offline. The reason is almost poetic. The crews cannot get to them, because the route crosses a tephra field southwest of the caldera that this eruption has buried too deeply. The volcano has been burying the equipment used to watch the volcano. So here is your watch list. These are the specific, real signals that the next chapter has begun in the order you should expect them. First, watch the tilt. If inflation resumes cleanly and stays smooth, the window will hold or tighten. If it goes flat again or reverses, the window slides later, and you now know exactly why, which puts you ahead of most of the coverage you will read. Second, watch for low-level precursory activity at the vents. Spattering, gas jetting, small overflows of lava creeping out onto the crater floor. That was the tell before episode 51, and before many episodes before it. It can start hours to days ahead of the fountains. Third, watch the alert level. When the observatory believes fountaining is imminent, they raise Kilauea from advisory to watch and the aviation color code from yellow to orange, and they publish a volcanic activity notice saying so. That change is the clearest single signal available to the public that the wait is nearly over. Fourth, watch the wind. If the fountains start while winds are pushing the plume northeast over the volcano area and Highway 11, this becomes a community story about masks, catchment tanks, and closed roads. If the winds hold from the northeast and push everything southwest into the closed desert, most people on the island will experience it as glow on a webcam. And that is the honest close to this. Somewhere under Halemaumau, a chamber of molten rock is refilling toward a number it has hit 51 times. When it gets there, 2 vents in a closed crater will throw liquid rock 1,000 feet into the Hawaiian sky, and 3 live cameras will be pointed at it, and a geophysicist in Hilo will check whether her model got the day right. The observatory's current window closes on the 31st of July. If episode 52 arrives inside it, that is 52 for 52 on the most improbable forecasting streak in the history of volcanology. If it arrives late or early, or if the pattern that has held since episode 5 finally breaks, that is the bigger story, because it would mean the plumbing under Kilauea has changed, and the clock everyone has been reading would stop being readable. Either way, we find out this week. Subscribe and turn on the bell, and when the observatory raises that alert level from advisory to watch, you will already know what the number on the tiltmeter means and why it matters. The account is nearly full. Kilauea is quiet the way a held breath is quiet.